All right, so now we're going to, it's about a page. So now we're going to go ahead and establish Abel's theorem. And then if we have time, we'll do a quick example, because it's pretty easy once you understand how it works. So we've talked about the Wronskian already. This is kind of like another version of that and how we can use it. So we're going to start with this. So let's say we have the equation. Actually, let's start with, let's suppose that we have y1 and y2. And let's say that they are solutions of the differential equation y double prime plus p of x times y prime plus q of x times y equals 0, where p and q are continuous on some open interval I. So these are all the conditions we need. We just need a second order linear differential equation. We need to know that we have y1 and y2 as solutions to this equation. Abel's formula says that the Wronskian of y1 and y2 is just going to be some constant times e to the minus integral of p of x dx, which looks suspiciously like an integrating factor, except for this minus sign there. So let's see what's going on. Okay, furthermore, w is either 0 for all x values in I, or never 0. So it's either going to be 0 all the time or never 0. So here's the proof. So since we have that y1 and y2 are solutions, that means that I should, in theory, be able to plug in y1 into this, and it's going to equal 0, right? And if y2 is a solution, I should be able to plug y2 into the equation, and that's going to equal 0. So that means it's going to look something like this. That means that y1 double prime plus p times y1 prime plus q times y1 equals 0. And also y2 double prime plus p y2 prime plus q y2 equals 0. Okay, so this is just based on the fact that here's the equation we're trying to solve, but we know y1 and y2 are answers, then this needs to be true. Does everybody follow that? Okay. Now let's say we want to eliminate. So let's say we wanted to eliminate what we have going on here. Okay, not the derivative terms, but let's say we want to cancel out this y1 and this y2. I could multiply this one by negative y2, and I could multiply this equation by y1. Okay, and then add. So if I multiply by negative y2 and by y1 and add everything up, okay, and then we're going to get y1 double prime. Actually, that's negative y1 double prime, sorry, times y2, and then plus y1 y2 double prime. What's that? So that's from the first term, right? Okay. Plus, now here we'll have a p term, And then that coefficient is going to be y1 prime, that'll also be negative, sorry, y1 prime times y2 plus y1, y2 prime. And now these cancel out, right? Because these will be exactly opposite. And then now we have this equal to 0. Okay, so does everybody understand where that's coming from? Okay, now let me just rewrite this without the negatives in the front. I didn't want to skip that step to make sure that everybody's following. I'm just reorganizing here. So this is the same as y1, y2 double prime minus y1 double prime is y2 plus p times y1, y2 prime minus y1 prime times y2. That equals 0. Okay. Now, off to the side, in case you don't recognize it, let's show what the Wronskian is again. What would the Wronskian for y1, y2 be if we wrote out the formula for it? So y1, you said y1 prime, or sorry, y1, y2 prime minus, I'll go in order, but y1 prime and then y2. Where do you see that in here? So this is just the Wronskian over here. Make sense? Okay. Any guesses as to what this is going to be? I mean, it's hard to see this, but what do we see in here? What derivatives are these? This is just the derivative of the Wronskian. Okay? So this over here ends up being the derivative of the Wronskian. And if you're not seeing that, I don't blame you. Because if you actually found the derivative of this, w prime, if you'd have to do the product rule, right? But what's going to happen is a couple of those terms end up canceling out, and these are the two terms that are left. Does that make sense? I'm going to skip that because I know you guys can do the calculus there, but so you just need to remember that this actually is w prime, okay? Well, let's see. How do you guys want to approach this? We're trying to find w now, right? We can solve this a couple of different ways. Integrating factor? Sure, it's linear, so why not? So the integrating factor would be e to the integral of p dx, right? And so then this equation on the left-hand side becomes w times the integrating factor, prime, right? On the right-hand side, it's 0, so multiplying by the integrating factor isn't going to change anything. And now when you take the integral, you get the Wronskian times the integrating factor is equal to some constant, right? And if we isolate the Wronskian, we're just going to move this to the other side, and we get c e to the integral of p dx, okay? Oh, yeah, I was like, that's not the right answer. Messed up the last step. And yeah, that should be negative now. And that's exactly what we needed to show. I just dropped the of x notation because I was a little lazy. But that's exactly what we need to establish. Okay? Now, so this is good. That establishes the theorem. Now, the one thing that is worth mentioning is that this over here, this leading coefficient was always 1, right? So don't fall for a trap where like you have something here and then you're just going to go straight and do the formula. This needs to be a leading coefficient of 1 before you can use this, okay? Also, let's talk about this. This last point that the Wronskian is either 0 for all x or never 0, right? Well, I think this is clear. If c is 0, then it is 0 for everything, right? But if this constant is anything but, that exponential is never going to be 0. Okay, so that clarifies that. Let's go ahead and set up an example, and maybe we'll pick up with it tomorrow. Actually, no. I think we're good. I'll just let you guys do that in the homework. Okay. So that is Abel's theorem.